Here we're given that x is a uniformly distributed random variable and with parameters 3 and 6, right? So this is A and this is B because we know uniform random variable has two parameters A and B where it's defined. Basically, these are the endpoints of the interval over which it is defined. In this case, it's 3 and 6. So in the first part, you want to graph the PDF of x. So we know over here, x is uniformly distributed with parameters A, which is equal to 3, and B, which is equal to 6, right? So these are the endpoints of the interval over which it is defined. And we know the way we can write the PDF of this uniform random variable, you know, for any uniform random variable, it's 1 by B minus A. So it's 1 by 6 minus 3 is 1 by 3 for x between A and B, which is 3 and 6. And it's 0 otherwise. Right, so here's something that we should keep in mind that is important. Okay, something we should note is x only takes values between 3 and 6, where PDF is non-zero. Now, why is this important? This is so why is this the case? Because wherever the PDF is 0, when you integrate the PDF over that interval in order to find the probability that x lies in the interval, you will get 0, right? Because whenever you're finding an integral of a definite integral of 0 where you plug in the limit, so the answer is 0, right? So like if you do a b 0 dx, this would turn out to be 0, right? Because this would just be a right, this would just be a 0, right? Right, so that makes sense. So basically the idea over here is that the first thing to keep in mind over here is this uniform random variable, which whatever interval of values it will take are going to be between 3 and 6 because that's where its PDF is non-zero. Right, so now when we want to plot this PDF, the way we're going to do that is going to be the way we're going to plot this PDF is now going to be that if we just plot this, then the way we are going to be plotting this. So here we're going to take small x, which are small x represents the values the random variable capital X takes, and this is going to be fx of x. So the way we're going to plot it is we know okay between 3 to 6 it is taking values 1 by 3. So we're going to make it like this. So between 3 to 6, the value of the PDF is 1 by 3, right? Between 3 to 6, and otherwise it is 0. So otherwise it is 0 like this, right? So this is its PDF, right? Okay, it's 3. This is a little messy, but the idea, okay, let me just erase this. So basically here it's 0 and here it's 3 and between 3 by 3 and 6 it's just 1 by 3. So this is its PDF. Okay, let's look at part B. Find the probability that x is less than 5. So we know we can answer any probability question using the PDF because area under the PDF gives us probability. And we know we can find the area under the curve using integrals, right? So essentially how I'll notice I can rewrite this as probability x is between 3 and 5. Why can I write it like this? Because just we discussed before that it's going to take values between 3 and 6, right? It's going to take values between 3 and 6 where 3DF is non-zero. So that's what's important to keep in mind, the universe over which your random variable is defined, because then we can be more precise about the probability we want. So probability x is less than 5 is essentially the probability x is between 3 and 5. So we don't have to worry about whether this is greater than equal to, less than equal to, because we know with continuous random variable, point probabilities are 0. The probability so x is equal to small a is just 0 for any value a, right? Because the point probabilities are 0, so we don't have to worry about equal to signs. So again, this comes from the fact that x only takes values between 3 and 6. So it can only take in values between 3 and 6. So the interval probabilities we consider are between 3 and 6. So now I know the PDF is 3 to 5. And what is the PDF? You know the PDF is 1 by 3. We're just integrating. And this would be obviously very simple. This is x, this is 3, this is 5. So this would just be 1 by 3. 5 minus 3 is 2 by 3. Another way you could have done this was, this is one way we could have found this probability, or just see from the graph, as area under PDF gives probability, right? And we know area under PDF gives us probability, right? So we could have just seen from the graph as well. Right? What do I mean by that? Because we know, like we said, the area under PDF gives us probability, and over here with uniform random variable, the PDF is just in a form of a rectangle, right? So it's very easy to see, to find the area of a rectangle. You can just use its PDF diagrammatically to find this area. We know this is 1 by 3. This is 3, this is 6. Now what I want is, I want to find the probability x is less than 5. Let's say 5 is somewhere here. So essentially I want to find this probability. Like you said, this is the probability x is between 3 and 5. Now this is 1 by 3. And this, sorry, no, this is not 1 by 3. This is 5 minus 3, 2. And this is 1 by 3. So this area is the probability x is less than 5 is equal to 1 by 3 into 2 is 2 by 3. So if you want to find the probability of a uniform random variable, one option is, just like for other continuous random variables, you can integrate its PDF. Or because its PDF is just in the form of a rectangular region, and you know area under PDF gives us probability, and finding the area of a rectangle is very easy. We can just directly find its probabilities from its diagram as well, from its diagram of its PDF as well.